All right, so please let me know if you have any difficulties hearing me. My name is Nicole, and I'm one of the academic advisors with the College of Engineering. So if you do end up coming to UAA, you would work with me through your first 30 credits. So we are very happy we have you here, and we have a great presentation in store. Before we get started, I do want to just go over some quick Zoom etiquette. So while we are going through the presentations, please keep your volume on mute, just so if you have any background noise, it's not interrupting. And you may keep your camera off if you'd like to. If you have a bunch of stuff going on around you, that's fine as well. Our event today is going to be broken up into 3 parts. We have Dr. Neumayer here from our computer science department, and he is going to do an engaging demonstration and then talk to you about our computer science department. And then we'll have time at the end for questions and answers. Okay, does anybody have any questions before we get started? All right, well, I'm going to turn it over to Dr. Neumayer.
Thank you for that introduction, Nicole. So again, my name's Seb Neumayer, and I'm a professor here at UAA in the Computer Science and Computer Engineering department. And so I have sort of some fun computer science related activities that I want to go through with you guys for maybe 15 minutes or so. And then from there, I just want to tell you a little bit more about our department. And so most of the thing I'm going to share with you is through a PowerPoint, and I'm going to be writing on the slides. So I'm going to share my screen, and can everyone let me know if you can see my screen, my PowerPoint? I'm just going to bring up the chat on the side here. Okay. All right, so it looks like I'm getting some messages that people can see it. So that's good. And so what I just want to tell you first a little bit about myself. And so I've been at UAA 3.5 years now in the computer science, computer engineering department in the College of Engineering here. I did my undergrad at the University of Illinois, and I got my PhD at MIT. And I'm very interested in network reliability, which we're going to see a little bit of today, cybersecurity, and cryptocurrencies. And so I teach a class on Bitcoin in the department. It's kind of one of my hobbies. It's very interesting academically. You know, it's been in the news a lot recently, so that's pretty cool. So it's definitely one of my interests, and it's very related to computer science. There's a lot of interesting academic problems there. But we're not going to really talk about that today. We are going to talk about really what computer science and engineering is. So I'm first going to give you sort of a flavor of some of the stuff that you would see as a computer scientist. And so computer science is really all about data. And so you want to transfer data, say, from one location to another. And so, you know, a couple of decades ago, the way you would do that is you would have a modem that would have, so you'd place a telephone, computer signal will go over a telephone line. And on that telephone line, you know, there's a phone here and a phone here. And then on that computer line, a series of beeps and boops would sort of go over the phone line. If you've ever picked up the phone line from a modem in the 1980s, it just sounds like that's because of zeros and ones are being sent over the phone line at an extremely high rate. And so this is the way that information is represented in a digital form. And maybe I want to pause and I'll make the comment. I think someone's trying to speak. And so if you have any questions, just feel free to speak up. I want this to be as interactive as possible. So maybe I'll wait for 5 seconds. Did anyone have a question? Okay, so as you know, we transfer this information from one source to another. you know, these bits can represent interesting pieces of information. So for example, these 8 bits here could represent the letter A, and maybe the next 8 bits could represent the letter T. And so you can see that these 16 bits would start representing, say, a word, at, right? And so from that and everything else that goes on the computer, you can, you know, part of it is you can make games and you can program them. So some of our faculty members, Kenrick Mock, our current dean, he's made the game Acrophobia. You can play this online. So this is something made by UAA professors, pretty cool. So what else are computer scientists interested in? And what do we do? Well, some of the places that we've worked, so I've worked at Lincoln Laboratory, which is a research lab out in Massachusetts. Several of our faculty members have worked at Intel. So Intel is a company which builds the chips inside the computers. Some have worked at Apple, which I'm sure you've all have heard of. Others have worked at other research labs like Los Alamos or NASA, as well as other firms. Okay, so I first want to talk about error detection and correction. And so going back, I told you that there's these modems that transmit these ones and zeros, but these modems aren't perfect. Sometimes there's a bit flip, so the 0 might get flipped to a 1. And if it did, if this represented A, well, if that bit flips, maybe that A is no longer represented. Maybe it now represents a Z. And that's not what we originally intended to be sent to the receiver. So how do we detect and correct these errors? So this is a fundamental sort of communication problem. And we already kind of do this. So you can imagine if you're in a loud party, if you're in a party somewhere or a large family gathering, and it's super loud, and you know, maybe your uncle is trying to talk to you and he's whispering and his signal strength is very low. Maybe you didn't hear one of his words. And if you didn't hear one of his words, maybe you didn't understand what the whole sentence really means. And so you might need to ask, hey, what did you mean by that? Or can you repeat your sentence? And so we already have this built-in error detection and correction. We just ask the person to repeat themselves. But in computers, we can often do a little bit better. And so there's a scheme here that I'm going to show you for error detection. So consider an array of a grid of 5 by 5 bits. So let's say that we have I'm just going to create an array of 5 by 5 bits here. 0, 1, 1, 1, 0, 1, 1. So this is just 25 ones and zeros. Like this. And so this is what we want to send. And so the way we send this securely is by adding a 6th row and a 6th column. Well, what we're going to add to that 6th row and 6th column is we're going to ensure that the rows have an even number of ones. Even number of ones. And so this row, for example, already has 2 ones. And so we don't want to add a 3rd one because that would make it odd. So we'd have an additional 0 here. Whereas this 2nd row has 3 ones. And so we would want an additional 1 to bring it up to 4 ones. And so we want even parity. We want an even number of ones on all the rows as well as all the columns. And so I'll keep going. The 3rd row should have its parity bit set to 0. So it has an even number of ones in the 3rd row. The 4th row should also be set to 0 because again, we have 4 ones already. And the 5th row should be set to, that should be a 1 so that there's an even number of ones on the last row. Okay, and we're going to do the same thing, but now we're also going to do it for the columns. And so for the columns here, we have 2 ones. And so this row right here, this column needs a 0. This column needs a 0 to keep the number of ones in this column even. And I'm just going to keep going. And so we have a 0 here, 0. So it turns out we need all zeros on the bottom because we are already all even. And so With this scheme, we can detect the location of a single bit flip because we can check every row and column, and every one of them should have an even number of ones. And if any one of them has an odd number of ones, we know that an error has occurred in that column. And so as an interactive exercise, can someone tell me here, I think you can maybe mark on the screen. You can someone mark or tell me, just you can type it in chat too, which one of these bits has been flipped? Go ahead and just talk and discuss or tell me where it might be. Someone's saying the fourth column or the fourth row. So fourth row, okay, yeah, someone circled it right here. And so that's exactly right. It's in the fourth row and the third column. And why is that? Because this row has 3 parity bits and this column has 5 parity bits, and 5 and 3 are both odd. And so you know that that bit has been flipped. It's not right. So that's pretty cool that the receiver is able to tell where the error occurred just by looking at the ones and zeros. And so my question then, sorry, hold on, I'm trying to figure something out. My question is, when would this scheme not work? So we can detect one bit flip and fix it. What would go wrong if we had 2 bit flips? Let's go back and take a look. So
if we
go on.
If we had 2, then if we flip one, the other one could be right if we flip the first one.
Right, exactly. So what happens in addition to this bit being flipped? This bit was flipped. So this 1 was actually a 0. And now when we go and do our parity check on this column, we see that we have 4 ones. And so we think that it's all good, but it's actually not all good. It's very far from it because we had 2 errors. And because we had 2 errors, we did not detect anything wrong. And so the way we could address this is add more parity bits. And that brings you essentially to something that's known as Hamming codes. And this is sort of the first stage of error correcting codes. And so if you have something like a CD player, on a CD player, you do something very similar. The actual information in this 5x5 grid is really there. And then you have a whole bunch of redundant information, which is essentially analogous to these parity bits. But it's sort of a more complicated scheme, but the overall idea is basically the same. And so they use this from anything from CD error correction to satellite communication, because when you're sort of sending something from Mars or one of the outer planets, the signal is very weak. You're not sure if it's a 0 or a 1. Sometimes that bit gets flipped quite often. So you need very strong error correction for those types of applications. And so this is something that you would study in computer science. So computer science is not just programming, it's also these conceptual type of problems where it's like, how do you effectively communicate from one computer to another? That's not a programming problem, it's really a math problem. I would say computer science is more like applied math than it is programming. Okay, maybe I'll pause there. Does anyone have questions about this error detection and correction idea?
What causes these errors? I may have misheard this or like not heard it at all, but what causes the errors in the first place again?
Yeah, that's an excellent question. So, if our sender over here is sending 1s and 0s over time, these 1s and 0s are actually represented typically by a voltage level. So the signal that you're sending might look like this, 1 0 0 1, and then all zeros, and then maybe there's a couple ones. And so, you know, the signal, there's a channel between the sender and the receiver. And it's not just any channel, it's like a noisy channel. So imagine if you were swimming in the ocean. You know, an ocean is not like a lake where you're not going to get thrown around. If you're swimming in the ocean during a storm, you're going to get thrown around, and random things you don't expect are going to happen. So that's going to essentially add noise to the signal. And it can add so much noise, maybe out here, that the noise looks to the receiver like it was a 1, but in fact, it was a 0 with some noise added to it. And so this noise just occurs naturally as sort of the signal is sent over a noisy channel. And
Thank you.
nature is inherently noisy. Like if you swim from one location to another, you know, in a wavy environment, you're gonna maybe get thrown off course a little bit. So that might be an analogy there. Good question. Any other questions? And so this is a pretty cool trick. You can even like show your friends this over Zoom. You can say, you know, you can have them like, you can say, oh, I can find the error in this. And you can sort of impress them with that cool party trick. Okay, so now I'm going to go and talk about another computer science idea. And this one is sort of has another analogy to it. So imagine that we have a city map. And when you have a city map, you're often, if you're a tourist, you're just interested in maybe some places that you want to visit in the city. Like there's a cathedral that might be cool. There's a castle over here, an art gallery, a science museum. And the buses only directly go from the hotel to the science museum, to the cathedral, and to the zoo. And if you wanted to get to the aquarium, well, you'd first have to go from the hotel to the cathedral, and then you take the bus from the cathedral to the aquarium. And so instead of mapping out the city streets, you can have this connectivity graph. So you can say, well, from the cathedral, where can you get to immediately? And so what I've described here, what I've showed you is what we call in computer science a graph. Now, this is different from the graph you may have seen in school, because in school, a graph would be like, oh, well, I have y is equal to x squared, and you would just draw the parabola. That's a graph. That's a graph of a function. But now we're graphing something else. So this is a graph. This is a connectivity graph. So what parts of the city are connected to other parts of the city? And so in this connectivity graph, we have the question. We're a tourist and we're starting at the hotel and we want to plan out our day and we want to take the least number of bus trips as possible because we don't want to pay a lot in bus fare. So how can we plan our trip so that we visit every single location and end up at the hotel? So I just described a day journey where I went to the science museum, to the toy shop, to the big wheel, waxworks, worship, castle, cathedral, and back home, but I've missed out on all this other stuff. So can people figure out a path that visits every single point on this graph, starting at the hotel and then ending back at the hotel? So you can just, you can tell me, you can either draw on the slide here to show it, or you can just type it in chat or speak up. So I'll let everyone think on that for 20 seconds or so.
Can I try?
Sure.
Do we go to the hotel and then science museum,
Okay.
toy shop,
Okay.
big wheel? Oh wait, no.
Yeah.
Wait, not that one. I mean, worship.
Okay.
And then castle,
Mm-hmm.
cathedral,
Mm-hmm.
aquarium,
Mm-hmm.
art gallery,
Yeah.
waxworks,
Okay.
big
I think
wheel.
I see where you're going.
Yeah.
Yeah, big. And then just all the way back home. Nice. Yeah. So that is a solution to this problem. It's one of many solutions. And so if you take that path, you get to see everything over the course of the entire day, and you end up back home. And so believe it or not, this is a fundamental problem in computer science. And so instead of viewing it as a city map, we're going to abstract the problem. Instead of calling it a cathedral, let's call it node 6. And instead of calling it a science museum, let's call it node 9. And so now we have each node has a number associated with it, and we have nodes connected to each other. And now we have a graph with labels instead of like words and places. They're now just numbers. And so we're moving up an abstraction level here. In computer science, we're all about abstraction levels and ever increasing abstraction levels. And so the question we were asking is the Hamiltonian cycle question. So can you visit every node on this graph and return back to the original one? In some graphs, you can't do that. In this one, you can't. Mark found an answer for us. So I'm going to give us another problem in computer science that maybe we can chew on for a little bit. It's the Knight's Tour problem. So imagine that we have a 5x5 chessboard. I think chess is getting pretty popular these days due to a good Netflix movie that came out. And so how does a knight work? Well, a knight is allowed to move forward 1 and then forward 2 and then over 1. And so a knight, which starts here, can go to these locations. And so a knight's tour, so imagine we're not going to consider these corner pieces. So it's sort of a chopped off chessboard. And so we're just going to consider these 12 squares here. So what we want to do is, can we find a knight's tour? So a knight which starts on square 1, we can move him to square 9, or we can move him to square 7, right? And so if we start here on square 1, we might say, okay, we're going to move the knight down to square 9 for a second step. And for our next step, we're going to move to square 3, and then we might go to, I don't know, square 11 for our fourth step. And so the challenge is, can you find a tour for the knight? So can you move the knight so that he visits every square and then comes back home? So I'll let everyone work on that for 20 seconds or so, and if someone has an answer, you can just go ahead and type it in chat or draw it on the screen or tell them.
I have a question.
Yes.
So, if we were to travel, would this entire spot count, or would it just be 1 and 9?
Excellent question. So you start here and you end there, so you'd only count 1 and 9 as being visited.
Thank you.
Might wait another 20 seconds or so. So if you have an answer, feel free to go ahead and broadcast it. Okay, I think Wesley might be trying to communicate a solution here. So
I got it, but I forgot the order I took. Oh shoot! Hold on.
that's a,
I think I got it.
okay.
So it would be 1, then I'd go
Okay.
to 7,
All right.
then I'll go to 5,
Yeah.
I'll go to 11,
Yeah.
go to 10,
Yeah.
and then it'll go to 4,
Mm-hmm.
and then it'll go to 12, then I'll go to 6, then I'll go to 8, I'll go to 2, then I'll go to 3, I'll go to 9, and then I'll go back to 1.
All right. That looked good to me. I think that's a valid solution. Now, let me ask everyone this. Did you find this to be a harder problem than the first city tour problem, visiting every location?
Yeah.
You did.
Yeah, it was hard.
So that's interesting. So I'm going to reformulate this problem like the following. So here's our Knights tour board. And so where can we go from square one? We can go to, well, we can go to square 7 and to square 9 and to square 6. So it's connected to square 7, square 9, and square 6, right? So I can make those connections. So I'm going to take it from a chessboard problem and I'm going to represent it as a graph. Does everyone see what I'm doing here? And then maybe from 6, you can move your knight to 8. So 6 is connected to the 8, and 6 is also connected to 1, which it already is, and it would also be connected to 12 like this, because you can go from 6 to 12. Okay, so if we go ahead and make that graph, well, it looks like this. Does that look familiar to you?
Yeah.
That's exactly the city map that we had before. And what we're trying to do on this graph is find the longest tour. And that's exactly what we're doing on this Knights tour. So by formulating the Knights tour problem into a graph problem, we can use our graph theory tools and then solve from there. And so it's often useful to sort of formulate problems into a graph problem because we can sort of think about them in an easier way. And so these two problems are actually fundamentally equivalent. They were just sort of set in different contexts. And so that's the idea behind some graph theory there. And so you can create these graphs, and graphs are everywhere. So here we had, Knights tour, or we had the city map. There's other things in your life which are graphs, like a family tree is a graph. So you're connected to your parents and your parents are connected to their parents. So you can imagine this graph of people that are connected to each other. And so the Knights tour is a well-studied problem. You can go read about it on Wikipedia. It's kind of an interesting problem. I won't talk about how to solve it generally, but here's a link in. If you go to this link, which I'll try to post the chat right now, you can view code which implements a solution to the Knights tour. And our dean, Kenrick Mock, wrote this. Okay, and now I realize I'm going a little bit slower than I intended, so I'm just going to sort of very briefly introduce a few other ideas in computer science. And again, everything that I've done so far, I haven't talked about programming at all. Programming is just a tool to study computer science problems. This computer science problem is really about graphs and these sort of math problems, like error correction code, and everything is. Graphs are everywhere. And so we really think about these abstractions, and programming is just a tool to study these abstractions. It's a necessary tool, though. Okay, and so other graph theory concepts that you might encounter is something called the minimum cut. And so I'll describe what the minimum cut is. I think I'll leave the maximum flow out. So the minimum cut between two pairs of nodes is a pretty, the minimum cut is just if I have two nodes, S and T in a graph, say this is the cathedral and this is the science museum. And we're looking at a graph now. how many road closures would be required in order to prevent you from going from the cathedral to the science museum? That is, what is the minimum number of links or roads in our network connecting places that would prevent you from having a path from one particular node to some other node? So what is the minimum number of construction projects required in order to shut down the city like that? Right, and so I have people are answering this in chat. This is great. So for this particular graph, to the minimum cut would be 2, because you would need to snip that link, and you separated them. There's another cut, like you could remove these 3 links, but that's a cut of size 3. And we're looking for the minimum cut, so we can just do it with 2. And so the minimum cut tells you something about the survivability of your network, because it tells you what is the minimum number of failures needed sort of for disconnection. And so this is a really important problem, especially in terms of security. And so this is a fiber map of the US internet. And so the backbone routers connecting sort of cities, the communication lines connecting cities are given their fiber optic cables. And these fiber optic cables, you can look at a map. And so you can look at this map as if it were a graph, because these cities are connected by fiber cables. So again, we're abstracting the internet backbone. You can imagine it as a graph, and you can ask the question, well, I have Seattle up here, and I want to make sure that Seattle talks to Washington, DC. And so you can ask, well, what is the minimum cut? What is the minimum number of fiber construction projects that would have to occur simultaneously, or disaster events that would occur simultaneously, like backhoes, construction projects? Anything could disrupt these links. But what is the minimum number that would sort of disrupt communication from the East Coast and West Coast of the US? So that's a very interesting sort of national security problem, but formulated as a graph theory problem, a computer science problem. And so, you know, here we are to find them in graph. You could just look and figure it out. But we need algorithms to do this. And so this entire field of study is, how do you find the minimum cut in a graph efficiently? And there's a similar concept called a maximum flow. I'm running late on time, so I can't really get into it, but it's kind of the analog to the minimum cut. And so I encourage you, if you're interested in these topics, go ahead, check out the Wikipedia articles on it, or you know, study computer science, and we definitely talk about them in our data structures course once you take a few programming courses. Okay, and I want to end my sort of presentation on my demo on the following. And so you may be familiar from, say, a robotics club, or just working with programming already. There's this concept of and OR gates. And if you've ever made a circuit, like soldered parts together, like diodes and LEDs, you may end up with a board that looks like this. And so this is a really great learning exercise to learn how these chip works, and how AND gates work, and how OR gates work. But in reality, you know, this is a very simple circuit. And as you sort of add functionality to your circuits, and you start adding and adding, and you make more adders, and maybe you're making more LEDs and making it more complicated, maybe integrate into your robotics stuff, well, your design starts looking like that. And that's not very friendly to debug. So if there's an error in here, a wire comes loose, good luck finding it. It's take you at least several hours to go and figure out what had just happened. So these hand-built designs are very error-prone. And so what I just described previously is computer science. Now what I'm describing now is more in the computer hardware side. So this is a computer engineering problem. So there's computer engineering is sort of how computers are actually physically built. And so we offer a course on field programmable gate arrays. And so they look like this thing right here. And so, and one of the problems, so an early Model T car, not Model T, but Thunderbird, Ford Thunderbird, does the following. So where they turn on their turn signal, and there's 3 lights that light up sequentially. And you can see that when the brake is pressed, you know, the one that's not the sort of the non-turn signal side lights up. And then when the other turn signal lights on, it goes 1, 2, 3, 1, 2, 3. And so that is how a Thunderbird tail light works. And so it turns out that you might want to implement this in a circuit. And if you do it with chips and wires, it'll probably look something like this. It's not exactly super straightforward. You need flip-flops, you need and OR gates. But this is not really how things are done in practice. This is a great learning tool, but once you get larger, you don't want to spend your time debugging. You want to spend your time making cooler stuff. And so that's where these FPGAs come into play. And so they're essentially programmable hardware. So instead of spending an hour building this, what happens if you could describe the circuit in sort of words or code? Then the computer will wire it up for you. And so that's what an FPGA is. And so that's what we focus on in this class. And so to make the T-Bird tail light, you would first make a state diagram. And then you would take that state diagram and write the corresponding Verilog code and then synthesize it to the board. And so to show you the end result of this, I'm going to switch over to the program, which allows me to synthesize. And I already have this project built, and I'm just going to program my FPGA. Oh no. Technical issue. Okay, I'm going to abandon this because it would take too long to figure out in real time, but it looks cool. You can imagine this board, it has LEDs. When I click this button up, the LEDs light up 1 LED, 2 LED, 3 LED. And so it has switches and LEDs. And so you can simulate that on this FPGA. And so that's the sort of stuff we would do in one of the computer science classes. This is more on the computer engineering side. Okay, so before I switch gears and start talking about the department for just a few minutes, does anyone have questions on any of the stuff we've seen so far?
Yes, I do. Do you know what that entire machine filled with wires was for?
So this one, I actually pulled this from the internet. I don't know what it was for, but I will tell you, when I was an undergrad, I took a computer engineering course where I had to build the computer not on an FPGA, but I had to build it on a breadboard like that. And my circuit did look like that. And it did have an error. And I think I spent like 5 hours looking for it.
Jeez.
And so, it's just not a very scalable way to build circuits. Okay, so what I want to do is spend the next few minutes or so talking about the department and what you could expect if as a computer science student at UAA. And so currently our department has 6 faculty members. Kenrick Mock, he's the current interim dean, but he still teaches a couple classes. Frank Moore, he's our department chair. Frank Whitmer, he studies a lot of environmental problems, so he writes a lot of code to study like tick habitats and things like that. Sean Butler, she focuses a lot on software engineering. Christoph Lauder, he focuses a lot on like numerical precision, things like that. And myself, and I like to focus on those type of graph theory problems I was talking about before. And so computer science and engineering, I think I gave you a pretty good flavor of some of the stuff that we sort of look at in our classes. But once you learn that stuff, what can you do with it? Well, you can, you can help program robots. There's biometric security. So how do you convert a fingerprint to a number? Autonomous cars, virtual reality. So there's a lot of computer graphics stuff and math that goes on in that. A lot of stuff that's just pretty cool, and a lot of stuff that hasn't been invented yet or still is really coming out. So things like cryptocurrencies, we have a class on. And yeah, and once you get out, there's plenty of companies that, I think computer science and computer engineering is a pretty in-demand field. So, there's Boston Robotics makes these robots, and plenty of communication companies, things like that. And so we really offer 2-degree programs. We offer a computer science program, and this is stuff like the graph theory I was talking about, and like error detection. And then there's the computer systems engineering, and this is the FPGA circuit and circuits stuff that I was talking about. But it's really a spectrum, and there's quite a bit of overlap with each other. So in either one you take, there's still plenty of classes. Like in both programs, you're going to start with programming classes and data structures, for example. But then you kind of differ from there. And so, like I was trying to mention, computer science versus computer systems engineering, there's 2 paths in our department. Computer scientists work with software, whereas the computer engineers, they're working with the hardware, like the FPGAs or the physical chips inside the computer. But again, like I was saying, there's tons of crossover. And so, if you have expertise in both, that's even more of a bonus for an employer. There is a bit of a difference in terms of the teamwork involved. So computer scientists, when you program, you can sometimes write programs in smaller teams. So you might be expected to work in a more office environment, because obviously you're not dealing with you just have a keyboard and that's it in a computer. Whereas a computer engineer, like you're going to need these circuit boards, or if you're doing more high frequency stuff, you might need more specialized equipment. And so because of that, you generally don't have the option to work from home. You generally work on larger teams because the projects are larger and require a lot more sort of engineering effort. Computer science, here's some of the classes you would be taking. So there's a class on databases, data science, like that graph theory stuff, as well as software engineering. So if you're working in teams and creating a larger project, how do you add to the project without overriding someone else's work? And so how do you integrate with the team? And so that's a large part of software engineering. Whereas computer systems engineering, you're sort of working with circuits and you're dealing with sort of the internals, how the computer is actually built at the silicon level. And so in terms of career options, computer scientists allows you to be a computer programmer, do database stuff, web developer. Whereas the computer engineering side, you're going to work with computer hardware. And then with either the degree, you can sort of helps you work in sort of the IT or the management information system stuff, or be an administrator, things like that. Maybe I'll just quickly, the job duties. Yeah, so example job duties, ensuring the security of a computer network. So maybe you'll be a network administrator. Or maybe you're maintain some database and build an interface for that, or develop software. Regardless, communication is going to be key, because if you build something that no one else can use because it's too confusing, or your code was written in too clever or confusing of a way, then it's not useful to anyone else. And so you need to learn how to communicate very well. And so giving presentations and learning how to write code so that others can read it is very important. And so at UAA, what does computer science and computer engineering look like? Well, in addition to the classes, we have a bunch of clubs. So we have the cybersecurity club, the robotics club. You can see the rover is pulling someone on a sled there. And we also, we used to have a computer science club. Since COVID, it's kind of gone defunct, but I imagine in future years, there's be a push to revive it. And the computer science club would just work on creating games or programs that they dream up. In addition, you could work with professors at UAA. And so here's a bunch of research projects that are going on or have gone on in the department. And so, like I was saying, Professor Whitmer, he has a map of tick habitats, and he's looking at how ticks are migrating throughout Alaska and might be spreading diseases. So that might incorporate a graph-like model, as well as other types of software engineering projects. I'm not going to enumerate them here. You can kind of quickly glance at them. But a lot of them are sort of Alaska motivated. like looking at how ice is receding from satellite images, things like that. Okay, in terms of your career and how much people are currently making, so the median wage for the computer technology industry is right now is 80,000. I mean, there's just paragraphs here, but that's the general idea. And then where do our grads from the UAA go? So they go and work at places like GCI, Alaska Department of Fish and Game. So there's plenty of local employers looking to hire grads. So Anchorage Wastewater Utility, Alaska Railroad. So you can just see all the different places some of our grads have gone. Some don't go immediately to industry. Some go actually to grad school. And so in grad school, you focus not on sort of the more general problems, you focus more on research problems. And so we had students go on to UCLA, Clemson, University of Utah, University of Alaska Fairbanks, and a whole bunch of others. And so skills our grads have told us that they use. Well, the main thing, unsurprisingly, is going to be programming languages. So Java, SQL, which is a database sort of programming language, JavaScript, so this is for web development, C++. So those are the main ones. And so those are skills you're probably going to want to sharpen at as an undergrad, maybe through internships before graduating to make yourself more marketable. And so with that, hope I gave a pretty good overview of the department as well as computer science. And so I'll just open it up to questions, or maybe Nicole, if you have any questions too, just let me know. But I'll stop my screen share now.
So if you have any questions, please feel free to unmute, ask away. If you have any academic questions, you're free to ask me. If you have any programming specific questions, I will deflect to Dr. Neumayer. So yeah, anybody have any questions? How many of you have never been to Anchorage and viewed the campus? My general work hours, 8 hours. What about you?
How long are programmer work hours in general? So it really depends where you go. So if you go to a larger company like Intel, or when I worked at Lincoln Lab, I was there 8 hours a day. But if you go to work at a startup, they're going to likely expect more out of you. And so I have friends working at startups, they're working like 12 hours a day, like they claim 6 days a week. And so that's really a more intensive, but then at the same time, there's a lot more upside if you go work at a startup.
Is there any other questions? Well, if after the event is over, if you come up with a few questions, feel free that you can reach out and contact us anytime. We'd be happy to answer your questions. If there's no more questions, we'll bring this to a close. We want to thank you very much for attending today. And remember, tomorrow is electrical engineering with engineering and music. And then Friday is mechanical engineering. So please feel free to reach out to us. And if you're planning on coming in the next year or so, please reach out to me as well. I'd be happy to schedule an appointment to help you get started.
And before we end, I do see an additional question in the chat. Someone is asking about their GPA and its significance in terms of going to industry. And so, or maybe continuing on to grad school. And I would say the GPA is important. You definitely want to do well in your classes. Employers looking for someone who put an effort to understand the underlying computer science concepts. But I would say, in addition to the GPA being important, what's also important is sort of having experience. And so using your summers while you're an undergrad to say, get an internship or work with a faculty member on some research projects and get sort of that more real world programming experience, that's going to make you a lot more marketable when you graduate. So
And-
I would say, in addition to focusing on the GPA, also focus on gaining experience.
And if you're also asking about GPA to enter the university, for a bachelor's degree program, you're going to want to make sure you have a graduating high school GPA of 2.5, just to be accepted into our university within a bachelor's degree program. And make sure you take math every year, even if you don't need it anymore, please continue to take it. It will significantly help you out once you are a student. So to apply for internships, I can tell you that we do get contacted from employers, and so we pass those internship opportunities on to the students. Generally speaking, what I most commonly see is students applying through internship job postings per se, whether they're with USAA Jobs because it's a federal internship position, or a corporation because it's a local internship position. So every university can handle those a little bit differently though. Sorry, I'm monitoring the chat just to see if there's any more questions. You're welcome. Is there any other questions?
All right. Well, I enjoyed letting everyone know about computer science, and yeah, thanks for listening, and I hope you learned something about computer science as well.
All right, everybody, have a great night, and hopefully we'll see you tomorrow.